Okay, in this video we are going to estimate population, probably should be estimating, population proportions. So we're going to look at an example which is about adult Americans and what proportion give blood. So how do we estimate the proportion of a population? Well, we take a sample. So we do a survey. And what we're looking at when we talk about proportions is a situation where you ask the participants in the survey, and they either answer yes or no. There's only two possibilities, yes or no. So here we have a survey of 2,306 American adults. This found that 417 had donated blood. In the last 2 years. Okay, sorry. I was thinking ahead. I almost put a question mark there. All right. So what proportion from the survey had donated blood? In the last 2 years. All right, so for our solution, I don't think we really need to watch a video or take a class. So for our solution, we're going to look at p hat, which is the sample proportion, and we say p hat. And then that's equal to x over n, which is the sample size in the denominator. And then in the numerator, that's the number who said yes to that question, which is, some people call that the success. Okay, so you get that. I'm going to do an estimate here and write that down as 0.18 or 18%. Now that is a sample, and the sample size is pretty big. So you think, well, should be pretty close. But saying things like it should be pretty close because it's large is maybe good in some cases, but we want to be more precise and present numbers and so forth in case you're arguing that you need money for your project or that a new drug works well or something like that. So it's not usually enough to say, yeah, I think it's going to work because of this, without backing it up with some hard numbers, because that's what people want. They want to put a number on something for how good your estimate is. Okay, so the standard deviation of the sample proportion is given by this, which I never proved, but it was in another video, and that's the square root of p 1 minus p over n. Because we don't know, since we don't know p, we use p hat. Now what's p? This is the proportion of the population. See, that's what we're trying to estimate. So there would be no way for us to know p. That's what we're trying to find. That's why we took our sample. So we're gonna use p hat, which is our 18% number, but I'm going to write it as, as 0.18. So that's the number we're going to use. And so for this problem, sigma p hat turned out to be the square root of 0.18, 1 minus 0.18 over the number n, 2306. Now the thing is that if I were what's probably better is for me to put 417 over 2003-06, but with my handheld calculator, that starts getting more difficult. See, you know, remember, 0.18 is the proportion of the people who gave blood for this sample. It is a rounded number, and if I could get away with it, if I felt like being more precise, I would put 417 over 2306, so I'm not rounding anything off. But then the practical matter is that I actually have to put that in my calculator, and when I do that, if I put too many numbers in, I sometimes have trouble. But on the other hand, maybe I could do it. Maybe I'm just not having enough confidence in myself. But anyway, I'm just going to put that number in there, and then already I'm having trouble. I did something wrong with the syntax. Oh, I see what I did. So, gosh. Well, this is real-time videos and the problems with that. Okay, I'm going to start over. So I have second square root 0.18 times 1 minus 0.18. I close that up, and then I'm going to divide by that sort of large number, 2306, and then I'm going to close that. Okay, I got something. That's really quite small. So that is about 0.8%. Okay, so that's the standard deviation of our sample proportion. Now, what I want to do then is say, well, what can we do with that sample proportion number? All right, so remember that the sample proportion p hat is normally distributed with its mean, which is mu p hat is p, and its standard deviation is this sigma p hat, which is square root of p 1 minus p over n, which what we've done is we have replace p by p hat. And then what I want to do is I want to draw a picture of this. And p is sitting here right in the middle. And then here I'm going to write down one standard deviation, p plus sigma p hat on one side, and then p minus sigma p hat on the other side. Okay, let's use the empirical rule to estimate some areas here. What I'm going to do is I am going to look at two standard deviations and see if we can remember that empirical rule. That number between two standard deviations is 95% of the population. Okay, so what does that mean, the population? That means that if I do this survey, if we do many of these surveys, which is unlikely that I can do that because it's such a large number, then 95% of the time, p hat is going to lie between p minus 2 sigma p hat and p plus 2 sigma p hat. That's 95% of the time. Okay, that is what the empirical rule says. So this is 2 standard deviations of the mean. Okay, now the thing is, I'm going to do a little algebra that's tricky, but that's what's going to happen. If I subtract p from both sides, I'm going to get p hat minus p. And in fact, instead of doing this algebra, we might just want to look at the picture. Okay, so what this is saying is if I take the difference between p hat and p, that difference is going to be greater than negative 2 standard deviations and less than 2 standard deviations 95% of the time. All right, so this is the difference between the sample and the true proportion. Okay, the differences between these numbers. The thing is, I'm going to do a little trick where I multiply through by -1, and when I do that, I'm going to change the direction and inequality, but actually it turns out we get the same thing, and it's easier to understand if I just talk that through, that the difference between p and p hat is between two standard deviations. All right, so what I did is I multiplied through by 1. So -1 times p hat is negative p hat, -1 times p is p. I multiplied these by negative, but if you remember, when you multiply by negative, you change the direction of the inequality. And now I'm going to add p hat, and then the result is I get p is between 2 sigma p hat. I'm going to get that p is between p hat plus 2 sigma p hat and p hat minus 2 sigma p hat. This is a 95% confidence interval. So why we call it confidence interval is that what this means is that I take my sample and I find p hat. What we say is we're 95% confident that the true value of the proportion of Americans who gave blood is between those numbers. It's not, p is a fixed amount. It's the true proportion of Americans who gave blood. And this is a confidence interval. It's how confident we are that the true value for p is within this interval. So for our problem, p hat was around 0.18 and sigma p hat was around, well, it's on another piece of paper somewhere. It's around 0.008. So therefore I can write 0.18 minus 2.008 less than or equal to p, and that's then 0.18 plus 2 times 0.008. So I'm just going to go ahead and take my calculator out. And that gives 0.164. The thing is, maybe I should have used another rounded to a more decimal place so I can get it better. But when I did this, anyway, I think this should be good. Actually, this number is, it's maybe better to round to 0.181, but okay, I'm not going to do that right now. So I get p. I can just tell you right now that really what we're going to do is we're going to get our TI-83 calculator to do this, so we don't have to fiddle around so much and worry whether I'm rounding it too much and so forth. I mean, even if I'm not using a somehow I want to use a computer, so I'm not. So see, the thing is, every time I round a number, I'm getting a little bit off, and then I think, well, should I round it here and there and all the stuff? It's better not to round off at all, and just because a computer can carry over large decimal numbers. But what we're having is that we are 95% confident that the proportion of adult Americans who gave blood is between, sorry, I ran out of space, 16.4% and 19.6%.